Hi, here we go, and I'll just open load up. It's a big old spreadsheet, so it takes a little bit of time. But I thought I'd start it off at the beginning rather than while I was in the spreadsheet, because sometimes it does have a habit of opening up on wherever it was left off. The first thing you do have to realize is it's packed with macros, so you need to turn the macros on. You need to be able to edit, and you need to be able to turn the macros on, and it should identify that in this kind of area. And as per usual, it's opened up where it left off. So basically just return to menu, and well, let's turn off the ribbons because we don't need the ribbons. And you will get that menu. Now we're going to be dealing with the loading program, which is this one here, and then that goes into that one, so it works out the loads of all of the various components: the roof, the ceiling, internal walls, floors, cavity walls, lean-to roofs, all of that malarkey. And then you will then input how much of those will be carried on your beam, and it will work out the UDL calculation. And from that point onwards, you then input it into your relative software. That's this part. All of this lot is, we'll discuss that another day, but this is just purely about the loading program. So if we press the loading, and then up will come this. Now you can see here that there's already data in there. Now the first thing you need to do is to clear all those entries, and there we go, we've cleared the entries. Now what this effectively does, this is the same diagram that's on the menu. It will calculate the load on there, on that beam, purlins, binders, or foundations, or in this, or ground beams, because that could quite easily be a ground beam rather than a strip foundation, a trench fill foundation. And it will also carry on and do eccentric foundations, but that's for another day. So let's assume we're going to do a ground beam, and we're going to do that ground, we'll do that ground beam there. So that ground beam is taking a block and beam floor there. It's taking part of this floor here. It's supporting that floor there. It's supporting that ceiling there, and it's supporting part of that roof there. Okay. So now we've just got to basically go through the elements that it supports. So the first thing it supports is a roof. So we've got two roofs here. We've got a standard roof and a lean-to roof, just in case, like on this beam here, it supports two roofs. So there's two roofs on there. In this case, it only supports one roof. Oh God, it takes all sorts, keeps pop-ups. So first of all, it's in yellow. We've got, if anything that's in yellow needs filling in, anything that's in lilac will have a drop-down menu. So that, I'm going to assume, we would put a protractor on that, but let's assume for argument's sake that is 25 degrees. So that's 25 degrees. Okay. And those tiles are Redland 49s. Now there's a generic concrete interlocking at 60 kilograms a square meter, which there is no concrete interlocking tiles that's as heavy as that. But if you go on to click on that, there's a drop down menu, and there's plain tiles, natural slate, artificial slates, go all the way down. Oh, I thought, because that should have thatch on it, because I said I'd do that for Isabel. Oh well, it hasn't. And what did I say? It has Redland 49. So there's Redland 49s. Up comes the weight at 51 kilos. Battens and felt is being identified as 6 kilos. Depending upon how far that roof span in, if it does make a difference if you have 4x2s, there's at 1.68, and 6x2s, 1.72. It makes a bit of difference what size rafters are on the roof. So if it's got purlins, it's generally 4x2, and if it hasn't got purlins, it's 6x2s. But leave it at 6x2s, I think that's fine. Then it says insulation. In this case, there's no insulation because it's the slope of the roof. The insulation's on the ceiling. So we'll take that 0 out. 1 layer of plasterboard, but you could quite have anything up to 4 layers of plasterboard if it was a sound resistant ceiling. But it's only 1 layer in this case. Oh, sorry, there's no plasterboard on this. What am I talking about? It's a normal roof with no plasterboard. And there's the load on plan at 76 kilograms a square meter. Obviously that multiplies up by gravity, 9.81. Acceleration due to gravity gives a permanent load of 0.75 kilonewtons a square meter. I said the design snow load is 0.75. That's old school, really. It should be 0.6. And there we go. So there's the roofing. Like I said, there's no second roof on it, so we don't have to worry about that. There is the ceiling joists, and they're likely to be around about 6x2s. But like I said, it's whatever's on the drawing. So we'll drop that down to 6x2s. Just 1 layer of plasterboard. Insulation, we'll kick that up to 5 kilograms a square meter. And there's the ceiling load. Okay, so we've got that. Now we move down to the floor. Floor timber, 22mm chipboard. We could have 18mm chipboard, but we won't. It's a proper job, this. And it's likely to be 250 timbers. Insulation, there'll be a bit of insulation in there for sound insulation. And in this case, there's only 1 layer of plasterboard, but if it was a fire-resistant ceiling, there could be 2 layers of plasterboard in there. And there's the loading for that. Let's go back to our diagram. Now we've got a block and beam in there on the floor construction block and beam. We got 75mm screed, but it could be any size screed. 50mm screed. Generally 75 goes on top of insulation. You get away with a 50mm screed if the insulation's below a ground bearing slab, for argument's sake, but this isn't. This is a block and beam. So there's the loading for that. Insulation, 3 kilograms a square meter. And then you have your various combinations. That's your general combination, a 150mm beam at 520 centres. That's with the blocks laid lengthwise. Then you could have a 15mm beam, but again, it depends upon what the specification. But you'll get away with that up to about 4 meters, that 150 at 520 centres. It's ground floor, so there'll be no plasterboard. So you put none in there. And there's your load. So there's your dead load or your permanent load in there, and your variable. That should be permanent and variable, I know. And that gives the load there. And then the only thing that's left that's on there, we put the roof in, we put the ceiling in, we put the floor in, we put that floor in, and now what's left is the external wall. So let's go down. Flat roof, that's not, it doesn't have one of them, doesn't have a balcony. Internal masonry, no. Internal lightweight, no. External wall cavity, yes. Now, it's facing brickwork, but it could quite easily be could be rendering. We'll put render on. We'll put render on there. And so that would be, say, a hemlite block, a medium density block. Insulation, medium density inside block. It says plus. We could quite have it, or we could have plasterboard on dabs, which is roughly the same weight. Could have dense plaster in there, which is much heavier. Need gypsum and skim, but that's your scheme there, and that's it. So we've got all the loads there. Now we've got to figure out how much is going down there. So if the say for argument's sake that's 8 meters from, let's say it's 8 meters from front to back, and it's 4 meters. That seems reasonable, but obviously this will be subject to you actually taking the measurements. So if that's, as you're well aware, all the roof loads is taken on plan, because we work it out on plan. Because there's the yeah, there's the load on slope, and there's the load on plan. So if that's 4 meters, then from there to there is 2 meters. Now you wouldn't just take from because of the purlin from there to there. You'll take from the purlin to the wall plate, because this part of the rafter still ends up going down in axial. So you would take from there to there. So there's 2 meters of roof load if that's 8 meters from side to side. So there's 2 meters of roof load going down that plate. So now you'd put in the attributed load, 2 meters. And then you go down to the ceiling, and again 2 meters, that's 4 meters from there to there, so that's 2 meters. So we put 2 meters of ceiling joist in there in the attributed load. Don't put it in the green, that's only if you need to split it inside leaf and outside leaf. Okay. Floor timber, we're still the same, roughly 2 meters. Floor, so there's 2 meters of timber floor on it, first floor. And there's a little bit more of, yeah, no, it's 2 meters of that on there as well. But again, it could be 2.1 meters, it could be 1.9 meters. But we put the 2 meters in there. And then that only leaves the external wall to put in. Now the external wall is going to be around about 5 meters. So it would be 2.3 plus, say, plus 0.3, that's 2.6, plus 2.3 takes you up to 4.9, and then probably another 3.3 on there, so it takes up to about 5.2. But again, you scale that off, or you measure it off, and you put your 5.2 in the attributed load. And again, you can run this all through by hand if you want. Cavity wall, where is it? There we go. So for the single UDL, you put that in there. Okay. And now you will now go back to the main menu, and you will then type UDL calculation, and it's all in there. So there's your permanent load, and there's your variable load, and there's your total load. About 40 kilonewtons a square meter. Quite typical for a 2-bed house. If it had a truss rafter roof on, it would be more as well, because instead of having 2 meters of roof on, it's 4. But there's all the loads. There's your first load, 2 meters. Remember, that was your permanent action. There's your variable action for the 0.6 and the 0.75. There was no second roof. Ceiling construction, again, there's the permanent, there's the variable multiplied by 2. Floor construction, 2 meters. There's your permanent action. There's your variable action, your imposed load of 1.5 kilonewtons a square meter. Your block and beam, there's your dead load, 3.71. There's your live load, or variable action, talking old money. No flat roof load, remember, so that's not there. and then you go to your cavity wall, external cavity wall, 5.2 times 4.22. It's only dead load, only permanent load. So those are your numbers. So at that point, you would then input that into your reinforced concrete beam software. Neurobeam has that. It's not the best, but when we check in, if you were designing, you would pump it into your software. If you check in, then you would then check the input data of the software. So that's basically how it works. There is a little bit of a I don't know if this is working well. If you do all of this kind of thing, just leave the X there. It'll take away all the stuff that's not relevant and leave you something that's printable. Same numbers, 32.47 and 4.7, and then back to your main menu. And that's basically it. The raft, the floor joist, we'll do the floor joist, that's easy. Anything in yellow needs to be input, so you might put 3.2 for the span, for your clear span, and then if you notice the effective span, I just add 100 for that, for the centers 0.4, but it could be 0.3. You may be putting two floor joists in between existing 600 trusses for a loft conversion, so you may end up with 0.3. So that you would put that in. You would put that in as a result of whatever's on the spec. This isn't a design piece of software. It's more of a check-in one, but it can be used as a design. Then you just check to make sure that the construction's right. In this case, it's 22mm chipboard, but like I said, there's many other deckings that you could use. Whatever the floor joists are for the floor joists of the floor. Number of plasterboard, it may be a sound resisting floor. If it's a sound resistant floor, it could have anything up to 4 layers of plasterboard on, 2 layers underneath the floor joist, and then another 2 layers on a suspended ceiling suspended from the floor joist. So you see all of this go up, but in this case it's not going to be. In most cases it's not. And even your variable load, you can have an office load in there, 2.5, shop 4, mezzanine floor in industrial premises 5, but it isn't, it's domestic, so it gives you 2. So but 3.2 but let's try it at 150 centers, and the joist satisfactory. Let's go down to 147s or 38s. Still satisfactory. It's doing well, to be fair. Let's try it at C16. There, it's gone over the top at C16. Where's it? It's okay on stress, which timber generally is. It generally fails on deflection. I don't think there's anything we can do. There's times you can put. Let's just for argument's sake, let's just take the plasterboard off. Look, I've put 12mm decking on instead of 22, and I've taken the plasterboard off, and the joists are okay. So these are the kind of variations that can make a difference. Obviously they were unrealistic variations, but sometimes changing it from 22mm chipboard where it's failed to 18mm and it passes. So you don't, with floor joists, you don't have this worry about the tables of which column to put it in. Whether you put it in the smaller, the below 50 kilograms a square. I think it's 20. Yeah, below 50 kilograms a square meter, between 50 and 75, and and 75, and whatever the tables say. If you wanted to check it against the tables, and this will be more economical, the tables, that's obviously the loading that the tables are looking for. And that's obviously built up from, that's all built up from that. Same thing goes for the rafters. There's the rafters. the same thing again. Sort out your loading. Might be, oh, there's the thatch. Oh, it's not in the, it's just in the, let's do Isabel's thatched roof. Wet thatch 50 kilograms a square meter. We're not going to use, the rafters aren't going to be that. They're going to be hundreds, and there's no plaster on them. Yeah, there is actually, because it's room in the roof. So there's the angle of the roof. So that's a construction. When we put the data in, slope, whatever the slope, so the slope might be 2.2 meters for argument's sake, and the pitch is probably about 45 degrees. If it could be anything up to 50 degrees if it's thatch. And here we go. If there's on the slope is 2.2. On plan it's only 1.51. Trigonometry, obviously don't have to explain that to you. There's the centres. We've tried 100 per 50s. See if that'll work at 2.4. It is, and I thought it would. 2.5, 2.6. And it's all down to the the angle of the angle, because the steeper the angle, the less it's got to work on plan. One thing I did identify, and it's a problem on low pitches. If you look at that 50-degree pitch, look at the horizontal force at the rafter foot at 0.49 of a kilonewton. If I drop that down out of daftness to 17 degrees. Look at the horizontal. That's way past a couple of nails. You need a bolted connection for that. So long rafters, you pump that up to 4 meters, which is not unusual, and putting 7x2 in, because people don't use purlins anymore. The reason why that's in there is because, yeah. And look at the, for a 4 meter long rafter at 17 degrees, look at the horizontal that the ceiling joist has got to take out. And if you've got a ring beam in there, the horizontal UDL that the ring beam will experience is 10 kilonewtons a meter. So it's substantial. Look at the vertical. The vertical's nowhere close. So long rafters that have a low pitch are a problem when it comes to connections. It shouldn't. It will exceed a couple of nails, or even a couple of timber locks. I don't know what a timber lock will do these days. I've got to do a bit of research on that. So that's that. So you can play around with it. Everything's in there. So there's rafter. Come on. Purlin 2, that situation's in there. Flat roof joists, floor joists if you've got a stud partition on top of it. So you go through exactly the same process, identify the floor construction and the centres, and then you would identify the partition loads, because if you have if it's subject to sound and there's a couple of layers on one side, then it'll bump the weight of it up. Like I said to you, those are all the load-ins, the unfactored load-ins for BS 5268, and the factored load-ins if you're going to use Eurobeam and EC. Is it EC3 or EC5? I can't remember it. Don't use it. I don't use the Eurocodes enough. That's all the data, and where it's highlighted, that's the data that's been used in that particular spreadsheet. But you would, if you only have to do that, you only have to go onto the formula and click, and that'll tell you exactly what cells the formulas are coming from. That one's failed as it happens. I'm not surprised. There you go. It's okay now. And that's it. The U values It's quite interesting stuff, but you'll have to play around with that. Like I say, I've got another video for that that I sent Trevor, and you can play with that to your heart's content. And that's it. That's a spreadsheet. And like I said, structure, U values, eccentric foundations, pad foundations, soakaway design. There's a soakaway design in there. It's a gem of a piece of a program, that. Unprotected areas, estimation of compartment temperatures. That's fire dynamics. And this little program, the spreadsheet I did, where if you enter the purpose groups, say if you enter an office and it's 3 stories, 4 stories, and it's, but obviously it won't be 5 meters high, it'll be less than 18, and there's, if it's, and then we've got to do this for the one for the floor office. So that's the fire resistance it needs. There's no limit on the compartmentation. 18 meter travel distance and 45 meter travel distances. Floor space factor 6 square meters per person. Fire alarm recommended L2. Risk profile for BS999 is A3. And that bit there relates to, it's not quite finished, this one, but a bit of work to do with it. But that's it. That's the spreadsheet. Okie dokie. Bye bye now.